Now we will define certain terms used in statistical mechanics. First of all, we will define microstate and macrostate. Macrostate of a system represents the macroscopic properties of the system which can be experimentally observed, and not the properties of individual particles of the system. Microstate of a system represents the microscopic property of the system, that is, properties of its individual particles. So macrostate is one which represent macroscopic properties of the system, and microstate is one which represent microscopic properties of the system. In microstate, we describe about its particles. For example, if we consider the distribution of 3 particles in 2 similar boxes, then there are 4 macrostates shown in this table: 0, 3, 1, 2, 2, 1, 3, 0. These are macrostates. These represents macroscopic property of the system. For example, macrostate 1, 2 represent that number of particles in first box is 1 and number of particles in second box is 2. It does not tell which particle is in box 1 and which particle is in box 2. When we talk about a particular particle, then the state is microstate. For example, if we have macrostate 1, 2, number of particle in box 1 is 1 and number of particles in box 2 is 2. Then there are 3 microstates are possible. First is, in first box we have particle A, in second box we have particle B and C. If we have in first box particle B, then in second box we have particles C and A. If we have particle C in box 1, then in box 2 we have particles A and B. So when we describe about particles of the system, then it is microstate. So for macrostate 1, 2, there are 3 microstates. Now consider a physical system composed of n identical particles in volume V. If there are ni particles having energy Ei, total energy E and total number of particles n are given as. Total energy E is given by summation NiEi and total number of particles capital N is given as summation Ni. Ni particles having energy Ei, it means that N1 particles have energy E1, N2 particles have energy E2, N3 particles have energy E3 and so on. So total energy capital E will be equal to N1 E1 plus N2 E2 plus N3 E3 and so on, and it is written as summation NiEi, summation over I. And similarly, total number of particles capital N will be equal to N1 plus N2 plus N3 and so on, and we write it as summation Ni, summation over I. The specification of the actual values of the parameters N, B, and E defines a macrostate of the given system. There will be a large number of different ways in which the total energy of the system can be distributed among the N particles. Each of these different ways specifies a microstate of the given system. Number 2, now we define accessible and non-accessible microstates. Accessible microstates of a system are those which are possible under the given restrictions. And and those microstates which are not possible under given restrictions are known as non-accessible microstates. Probability of a macrostate. Probability of a macrostate it is not probability of a microstate. We are defining probability of a macrostate. Probability of a macrostate is equal to the ratio of number of microstates corresponding to that macrostate to total number of microstates. That is, probability of ith macrostate Pi is equal to this ratio, number of microstates corresponding to macrostate divided by total number of microstates. So it is the ratio of number of microstates corresponding to that macrostate, which we write by omega I, and total number of microstates, which we write as summation omega I. So Pi is omega I upon summation omega I. Omega I is the number of microstates corresponding to that macrostate, and summation omega I is total number of microstates. 1 upon summation omega I is the probability of one microstate, which we write by small p. Then Pi is equal to omega I into small p. So Pi, probability of a macrostate, will be proportional to omega I. It will be proportional to the number of microstates corresponding to that macrostate. It is clear that Pi is proportional to omega I. That is, probability of a macrostate is proportional to the number of its corresponding microstates. Thermodynamic probability. Now we will define thermodynamic probability. Thermodynamic probability of a macrostate is equal to the number of microstates corresponding to that macrostate. So number of microstates corresponding to a given macrostate is known as thermodynamic probability. That is, thermodynamic probability W is equal to omega I. We write thermodynamic probability by W, and it is equal to omega I, which is the number of microstates corresponding to a given macrostate. For example, if we have to distribute n particles in many similar boxes, such that in box 1 number of particles is n1, in box 2 number of particles is n2, in box 3 number of particles is n3 and so on, then thermodynamic probability of the distribution n1, n2, n3 is given by W equal to factorial n upon factorial n1 into factorial n2 into factorial n3. So for this distribution n1, n2, n3, it means that in box 1 number of particles is n1, in box 2 number of particles is n2 and so on. Then number of microstates, which is thermodynamic probability W, is given by factorial n upon factorial n1 into factorial n2 into factorial n3. In numerator we have factorial n, it is factorial of total number of particles. In denominator we have factorial n1, which is the factorial of number of particles in box 1, then factorial n2, which is factorial of number of particles in box 2 and so on. Postulate of equal a priori probability. To a given macrostate of the system, there correspond a large number of microstates. If there are no other constraints, probability of each microstate is the same. So if we have a given macrostate, there are large number of microstates corresponding to this macrostate, and probability of each microstate will be the same. This is referred to as the postulate of equal a priori probabilities. Now we will define Gibbs ensemble. What is the concept of Gibbs ensemble? One or more independent parts combining together constitute a system. For example, if we have several particles, then they constitute a system. For example, gas molecules in a vessel. So there are many particles which are gas molecules, and if they are inside a vessel, then this vessel is known as a system of large number of gas molecules. For example, gas enclosed in a vessel. If we want to determine some macroscopic property of the system accurately, we have to make a large number of observations on this system and then find their average value. In each time when we take observation, initial conditions of the system must remain the same, which is very difficult. To avoid the difficulty, Gibbs suggested that instead of taking observations on a system at different times, we consider an ensemble of large number of identical systems and take observations on the same time and find the average value. So if we have a system and we want to know some physical property of this system, we take observation several times and then find its average value. If we have only one system, then we have to find the value of a physical property at different times. So the physical conditions, it is very difficult that physical condition of that system remains same at different times. So Gibbs suggested that we take large number of identical systems which form ensemble. So ensemble, Gibbs ensemble is a group of large number of identical systems, and we take observation at a particular time to all these identical systems. To avoid the difficulty, Gibbs suggested that instead of taking observations on a system at different times, we consider an ensemble of large number of identical systems and take observations on these systems, identical systems, at the same time, and then find the average value. Such ensemble of identical system is known as Gibbs ensemble or statistical ensemble. In Gibbs ensemble, all identical systems are not in a particular state, but these are distributed among all the accessible states. Now suppose we have to determine mean value of some microscopic property X of a system. It is macroscopic property X of a system. We want to find some macroscopic property X of a system. Then we consider ensemble of capital N identical systems. We take capital N identical system. Capital N is large number. So we have a large number of identical systems. This form ensemble. It is Gibbs ensemble or statistical ensemble. And out of these N identical systems, we find that in N1 systems, the value of X is X1 and the value of X is X2 in N2 systems. Value of X is X3 in N3 systems, and so on. So we have capital N identical systems, out of which in N1 the value of X is X1, in N2 value of X is X2, in N3 value of X is X3, and so on. Then mean value of X is given by this relation. Mean value of X is equal to N1 X1 plus N2 X2 plus N3 X3 and so on, divide by N1 plus N2 plus N3 and so on. It is equal to N1 X1 plus N2 X2 plus N3 X3 and so on, divide by capital N. N1 plus N2 plus N3 is equal to capital N, total number of systems. Now we can write it as N1 upon capital N into X1 plus N2 upon capital N into X2 and so on. N1 upon capital N is P1. It is the probability that value of X is X1, because total number of systems are capital N, and in N1 the value of X is X1. So N1 upon capital N is P1. It is the probability that value of X is X1. Similarly, N2 upon capital N is P2. it is the probability that value of x is x2, and so on. So average value of x is equal to p1 x1 plus p2 x2 plus p3 x3 and so on, and we can write it as summation pi xi. Now we have three types of ensembles: micro-canonical ensemble, canonical ensemble, and grand canonical ensemble. An ensemble, first we will define micro-canonical ensemble. An ensemble in which there are large number of independent identical systems having same energy E, same volume V, and same number of particles capital N is called micro-canonical ensemble. This is shown in this figure. It is the group of large number of identical systems, and all these systems have same values of E, V, and N. These systems have same energy E, same volume V, same number of particles capital N. In this ensemble, each system is separated from other by rigid, insulating, and non-permeable walls. The walls separating these systems are rigid. Because the walls are rigid, so volume V of each system remains the same. These walls are rigid, so the volume of each system remains the same. It is V. These walls are insulating, rigid, insulating, and non-permeable walls. These walls are insulating so that the energy of each system remains capital E, remains the same. And these walls are non-permeable. Non-permeable means no particle can goes from one system to other. So number of particles capital N remains the same. So E, V, and N are same for all these identical systems. For volume V remains same. We have these walls as rigid walls. For energy E remains the same. We have these walls as insulating walls, non-conducting walls. And for N remains same. These walls must be non-permeable. Next is canonical ensemble, a system in which there are large number of independent identical systems. It is not ensemble, it is ensemble. Ensemble, correct this, it is not ensemble, it is ensemble. Ensemble means group of identical systems. So ensemble in which there are large number of independent identical systems having same temperature T, same volume V, and same number of particles capital N. It is called the canonical ensemble. This is shown in this figure. Canonical ensemble is group of large number of identical systems having T, V, and N same, having same temperature T, same volume V, same number of particles capital N. So now we have volume same, so these walls separating the systems are rigid. Number of particles capital N is same, so these walls are non-permeable. And now we have temperature of all these systems is same, so these walls are now conducting walls. When walls are conducting, then temperature remains the same. Temperature of all these systems remains the same as capital T. And in last we have grand canonical ensemble, an ensemble in which there are large number of independent identical systems having same temperature T, same volume V and same chemical potential mu is called the grand canonical ensemble. It is shown in this figure. In grand canonical ensemble, these identical particles have same values of T, V and mu, same value of temperature T, same value of volume V and same value of chemical potential mu. So here volume is same, so these walls separating these systems are rigid. Temperature is same, so these walls are conducting walls. And now there is no restriction of number of particles is same, so these walls are permeable walls. Number of particles can goes from one system to other system.